Hi everybody, my name is Lee.
And my name is Valentin. We're with the Space and Terrestrial Autonomous Robotic Systems Lab, or STARS Lab, at the University of Toronto Institute for Aerospace Studies.
And we're here to tell you about our work on reducing drift in visual odometry by using a Bayesian convolutional neural network to infer the direction of the sun. So let's get into it. We trained a deep model to estimate both the direction of the sun and, importantly, a principled covariance for each estimate. This allowed us to straightforwardly integrate global orientation information into a standard feature-based stereo visual odometry pipeline without relying on extra sensors or special camera orientations. So how does global orientation information help us in VO? Well, since VO is a dead reckoning technique, it suffers from superlinear error growth as a function of distance traveled. This is mainly due to accumulated orientation error. If we incorporate absolute orientation information into the VO pipeline, we can restrict our error growth to be linear. A well-established way of doing this in the literature is to observe a known directional landmark like the sun. The sun is a convenient source of orientation information since it's easy to find and its motion in the sky is well understood. This is true not only here on Earth, but also on other planets in our solar system. For example, the Mars exploration rovers use their PanCam apparatus in a special orientation to periodically observe the sun and make corrections to the rover's trajectory. Other vehicles have used specialized sun sensor hardware to continuously estimate the sun direction and make more frequent corrections. Now, a natural question to ask is whether we actually need a hardware sun sensor or a specially oriented camera to use the sun this way. In other words, do we need to look directly at the sun to figure out where the sun is? What if instead we could take the same image stream that we're already using for VO and use it to infer the direction of the sun from a variety of visual cues? For example, in urban environments, we could look at things like illumination gradients in the sky, well-lit surfaces, specular reflections, and shadows, all of which should give us some information about where the sun might be in the sky. So what we would like to do is to find a model that can estimate the direction of the sun in 3D from a single RGB image. We would also like our model to give us an idea of how confident it is in its prediction, which would allow us to better incorporate this extra information into our VO estimator. The approach we took in this work was to train a Bayesian convolutional neural network to do exactly that. A Bayesian CNN works just like a regular CNN, but uses dropout layers at test time to make multiple stochastic passes through the network. This allows us to compute a posterior distribution over sun vectors from which we can extract a mean and a covariance. Our network, which we call Sun BCNN, is a modified GoogleNet architecture pre-trained on the MIT Places dataset with additional training on representative data. Looking at some of the learned convolutional filters in the network, we can see that they appear to fire on similar lighting cues to the ones we identified earlier.
So how do we train Sun BCNN? In this work, we used 10 sequences from the KITTI odometry benchmark. In total, this amounted to over 21 kilometers of urban driving data, from which we created 10 train and test pairs using a leave one out approach. In other words, we trained on 9 sequences and tested on the remaining 1. Each training set consisted of approximately 20,000 images. We labeled each image with a 3D ground truth sun vector. We computed this vector by querying a solar ephemeris model and transforming the expected direction of the sun into the local camera frame using the GPS INS poses. For our loss function, we minimized the cosine distance between the estimated and ground truth sun directions. The trained Sun BCNN models achieved median angular errors of less than 18 degrees for all 10 test sequences, but performed better on some sequences than others. Qualitatively, we found that Sun BCNN tended to be more accurate on images with strong directional illumination cues, such as the long shadows you can see in the upper pair of images, but tended to perform poorly in the presence of ambiguous illumination conditions, like those shown in the bottom image. Putting it all together, we incorporated Sun BCNN's estimated sun directions and corresponding covariances in our stereo VO pipeline and compared their effect on VO drift to several other single-image sun detection methods. Notice that the Sun BCNN estimate tracks the true sun direction quite well most of the time, but the estimates are often erratic from frame to frame. This is because Sun BCNN treats every image independently and does not have any notion of temporal consistency. In future work, we plan to investigate modifications to the network that allow it to account for the sequential nature of VO data. Looking at the final VO estimates at the bottom, we can see that incorporating information from visual sun detection can significantly reduce drift on long trajectories, and that Sun BCNN outperforms competing techniques. Thanks for watching. Please note that you can find a cafe-based implementation of Sun BCNN on GitHub, and for more videos like this, subscribe to the Untitled Stars YouTube channel.